everyone. My name is Taichi from Mitsubishi Research Institute in Japan. My research is focused on peat soil and peat forest modeling by using hyperspectral data. Peat forest has several problems. First problem is peatland. Peatland is rich soil carbon storage, and this is potential for large CO2 emission source. And if hydrological environment change is occurred, the groundwater level is decreased and the peat soil is drying. So this figure shows this phenomenon. And the second problem is forest degradation. Forest degradation is a major cause of forest fire and disturbance and poor growth vegetation and peat decomposition and so on. So we think that there are three demands for this problem. So one is developing technology to assess the carbon emission in peatland forest. Second is contributing MRV, measuring, reporting and verification. MRV development of REDD plus activity in peatland forest. And the third is about cost and method. Low cost method is better and high accuracy method is better too. So in this study, we think the solution is applying remote sensing data for monitoring forest condition. To monitor the peatland forest condition, we built the two kinds of the estimation model. First is this one, forest type classification model, and second is biomass estimation model. In this study, our objective is to develop the accurate classification model and biomass prediction model with remote sensing data, hyperspectral data. This is the outline of my research. First, this is input data. We used both of airborne hyperspectral data and field survey data. And second, methodology, we use the sparse regularization and the texture analysis. By using this input data and methodology, we built the prediction model. Two types of prediction model. First is the forest type classification, and second is the biomass estimation. After that, we compared results. We compared the new method with traditional method for validation. And finally, we calculated the output data. One is the forest type prediction map, and the second is the biomass estimation map. Survey area. We selected Hambangen in central Kalimantan in Indonesia. The Hambangen has many kinds of peat swamp forest and the large distributed area by forest fire in 1997 and 2002. In north part of Hambangen, there are large area of non-damaged forest. This is photo and this is map. And we use remote sensing data. We use hyperspectral data. Hyperspectral data was taken by airborne hyperspectral sensor HIMAP. We collected data on July 2011, and the hyperspectral data has 100 to 26 bands from 450 nanometer to over 2000 nanometer. And spatial resolution is 4.2 meter per pixel. This is a flight line, and this is a quick look map. Before the processing, we have to do atmospheric correction and BRDF correction. So ATCOL4 is used for atmospheric correction. In the case of the BRDF correction, we have several problems because of the sun sensor target geometry and the airborne sensor has a wide field of view. And This image has a difference of measuring time and condition. So please look at this. In the image, there are radiometric distortion in one line. And the second problem is the difference of average radiance. So in order to solve this problem, we developed the radiometric normalization algorithm. We applied that. This is before image and this is the after image. And about field survey, inside the airborne measurement area, we conducted field survey to collect for prediction model, collect for the training data. We had the two types of field survey. One is the tree species identification. We collected over 100 coordinate data. The specialists of tree species identified the species of each coordinate, main species to each coordinate. And after the survey, we divide all the species into three classes. One is density low, one is middle density, and one is higher density. After fire forest, the forest is recovering. So first step is density is low, and second is middle, and third is high. So the other survey is a quadrant survey. We make the quadrant square to 20 meter and 20 meter quadrant. And in the quadrant, we measure these items, species and DBH. DBH is the width of the tree, and the tree head and the crown cover and the underground water level. We did this survey in 33 quadrants. So by using this field data, we calculate biomass estimation by using this equation. This is methodology flow, modeling flow. Training data is here, hyperspectral data and field survey data. And the method is a supervised learning. In this study, we use the sparse regularization. And by using the data and method, we built the estimation model. One model is classification model, and second is a regression model for biomass. So why did we select the sparse regularization? So this is because the sparse regularization has 3 points of benefits. First point is optimal band selection. Ineffective parameter and ineffective bands will be removed from prediction model. And higher generalization capability. The prediction model with smaller number of bands achieves a loss over 15. Over 15 is very important problem for the supervised image, supervised learning. So third point is a more interpretable model. So by using sparse regularization, we use two types of estimation, two types of super learning methods. First is the loss regression as regression model, and second is the sparse linear discrimination analysis for classification. This is a theoretical overview. The sparse regularization adds penalty to loss function to obtain the model with small number of variables. This is the penalty coefficient. So, for classification model, we use optimal scoring. And the other methods for this study, we used texture analysis. This is because the in tropical area and subtropical area, the biomass level is very high, and the forest canopy is closed with multiple layering. And the forest has great diversity of species. So each pixel is not independent of its neighbors. So dependency is useful for identifying different aspects of forest stand, structure, and density. But the pixel-based approach is not enough to extract this information. So we use GLCM, one kind of texture analysis. Texture analysis can extract the information of dependence and take into spatial pattern, and texture analysis is very useful for classification of forest type and identifying canopy density. So this is prediction model, two types of prediction model. First model is a forest type classification model. This is the training data, and this is the method, and this is the estimation model. In training data, we use the spectral data, both spectral data and texture data. Same as classification model, in the biomass estimation model, we use both spectral data and texture data, and field survey data. So this slide shows the experimental setting. So forest type classification model, our target is three classes. One is a mixed forest consistent of large diameter trees. This is a high density forest. Second is maybe tsumi. Tsumi is a low density forest, just like that. So the three is a mixed forest consisting of small diameter trees. This is a middle density forest. And we use spectral hyperspectral data, spectral data and texture data, and field survey data. Plus 1 is 32 sample, and plus 2 is 62 sample, and plus 3 is 40 sample. For validation, we conducted two types of tests. First is a closed test. In closed test, training data is all sample, and validation data is same, all sample. And next, the open test. In open test, training data is 4/5 of all data, and validation is remaining 1/5 of all data. This is randomly choice. So we did the 5-time iteration for this validation. And for comparison, to compare this new method to this new method with other method. So we use a classification model by using only spectral data. New method uses both texture and spectral data, but we use spectral data for comparison. This is the result. Left side is closed test, and right side is open test. Left side is very similar, very similar, the same result. But please look at this. In open test, the only reflectance data is not enough accuracy, but the combined model achieves a high performance, over 19% prediction accuracy. This is a result of prediction map. Left side image is used only reflectance data, and right side is used combined data. So combined model can identify the class clearly, very clear. And according to the field survey, this prediction map is in almost agreement with on-site condition. Same as the classification model, we conducted biomass estimation model. Dataset is here. Target value is biomass, and we use the hyperspectral data, spectral data and texture data. And we use the field survey data of 33 quadrant. So for validation, we did the 1,000 times 5 fifth-fold plus validation for the estimation model. And for comparison, we use the LDSI, normal difference spectral index, as a traditional method. By using this, highest correlation 2-band was selected for biomass estimation. 2-band is here. 750 nanometer and 789 nanometer. By using 2-band, built a linear regression model for biomass with 2 bands. This is the result. LDSI model is red plot. LDSI is green plot. So LDSI, the traditional model, is low accuracy in estimation for over 300 ton per hectare of biomass. But on the other side, LASSO is this new method by using spectral and texture data, achieve a possibility to predict biomass over 300 with high accuracy. This is the result of biomass estimation map by using last regression. So prediction map by last model corresponded close to on-site condition. Conclusion. I present two types of forest monitoring method. First is the forest type classification, and second is biomass estimation. Our method has two advantages. One is high accuracy. This is because we use both spectral and texture information. And second is the generalization and optimal band selection. This is because we use the sparse regularization. And our method has potential for contributing peatland RDD plus activities. And this research contributes for the application of space-borne hyperspectral sensor data, such as history and so on. This sheet shows the history hyperspectral image suite. Ministry of Economy Trade and Industry of Japan in Japan are developing this sensor. Thank you.
So questions for your chair, your other chair. I don't have a question for the chair, so we may have to thank the chair for his talk. Now, is the fifth speaker here? The last speaker? Yeah, your thing isn't up here. Your presentation's not in the... I don't think his talk is in the folder. Yeah. Yeah, but I don't think it's there. Go down to the folder. Oh, yeah.
This one, right?
Yep, okay, great.